Hello class, I hope you're doing well today. Today we're going to continue on our discussion of evolution. So to review, last class we talked about some of the history of evolutionary thought, as well as natural selection and the other agents for evolutionary change. Today we're going to start to delve into some of the evidences for evolution. So let's get started. One of the very important lines of evidence for Darwin was the idea of artificial selection. And when we talk about artificial selection, we're talking about instead of the natural world deciding which organisms survive and reproduce, it's humans that decide which individuals survive and reproduce. So this is what's given rise to the variety of dogs, for example, starting off with the wolf. Now, this was very important for Darwin because he could easily see how selection could lead to significant changes in organisms in a relatively short period of time. So it really wasn't a stretch to think that the natural world could play that same selective force. But let's not get narrowed down to thinking that it's just animals that this applies to. We've applied this to other, certainly plant crops as well. So here we have teosite. This would be the ancestor to corn and giving rise through selective breeding to what we have today. And we can also take a look at from the common mustard plant. Our ancestors have selected it for a variety of traits that have led to all of these variations from the ancestral mustard plant. Again, this is all through selective breeding or artificial selection, shall we say. Probably the most obvious line of evidence, or what we think of as the most important line of evidence, is the fossil record. This is probably what we get to in our minds when we think about evidences to begin with. So when we want to think about this, we want to first explore how we find these fossils. Typically, they are embedded in layers of rock, which we refer to as strata. And as we look at strata from a geological standpoint, those strata that are further down in the rock are going to be older than those strata that are closer to the surface. And we can do a process of relative dating by comparing the ages of fossils in one layer versus the other, knowing that the layer that's deeper down is older than the layer that is closer to the surface. Again, that's referred to as relative dating. Now, the fossil record is wonderful because it shows us how organisms have changed over the history of time. If we go back to the most ancient rocks that we find on Earth, we can find rocks that were produced when oxygen levels were very low in the atmosphere. And in fact, before there would have been life present at all. And then we have evidence of oxygen being produced into the atmosphere. We have fossils of microbial life early on. We eventually get to animals. And we see this change in animals. First, all life was in the ocean, where we have invertebrates primarily. Then we see these changes where eventually vertebrates come along, the fishes. Later on, we see evolution of the amphibians, the reptiles, and the small mammals eventually coming about. Finally, we have the birds and dinosaurs present. And then about 65 million years ago, we had an event occur where a meteor struck the Earth, causing a global catastrophe in terms of climate change, led to extinction of the dinosaurs, bringing in the age of the mammals. So the mammals began to flourish, and it really isn't until fairly recently that humans have been on the scene. So we're just a portion of time in this whole profile. If we go back beyond several million years ago, we will not find human remains, say back in the time of the dinosaurs or before then. So this really is a kind of a guidebook on how life has changed over the history of time. We can also do absolute dating on these strata of rock. So by looking at certain isotopes, chemical isotopes, we can then compare them, and knowing how long those isotopes are present, we can determine the absolute age of rocks. So the type of radioisotope dating that we're most commonly used to, or you usually hear about, is carbon-14 dating. Now, carbon-14, when it undergoes radioactive decay, it becomes nitrogen. So we're going to look at how much carbon-14 is present in a specimen compared to nitrogen. And by looking at the, knowing that the half-life of carbon-14 is about 5,730 years, and we can then understand that if we had 100% carbon-14 over a period of 5,730 years, we'd have that reduced to 50% carbon-14. And this is very useful when we're looking at anthropology, so the history of human work. So from 100 years ago to 30,000 years ago. If we want to go back farther, say look at things in more ancient times, then we have to use different radioisotopes. So we might make use of potassium-argon dating. So if we're looking at dinosaur remains, we might make use of potassium-argon dating. Or if we're looking at the age of the Earth, then we might get into uranium as the isotope that we're using. So again, the idea is that over the period of one half-life, this is the time period for all of the parent isotope, shown in red here, to undergo radioactive decay to the daughter isotope. And again, once we have over the period of one half-life, half of that isotope will be broken down. So here we have 50% of the parent isotope. After a second half-life, whichever time period that may be, we are down to 1/4, 1/8, 1/16, so forth. So this is a mechanism by which we can determine the absolute age of a specimen. So when we're thinking about fossils, not only can we date them, but they are very important because they show us what these organisms that are long since extinct, what they were like. So we wouldn't know about things like the Brontosaurus had we not had these remains. Other things we would not have known about, trilobites, the allosaur. Here we've got the stegosaurs, or the pachycephalosaurs. All of these organisms we know of because of their fossil remains. And fossil record does indeed show us how organisms changed over time. So one of the things we want to be aware of is the petrification process. How did those fossilized remains form? And when we talk about petrification, so when we're looking at dinosaur bones, they are formed through petrification, or what's also known as permineralization. And several things have to happen for this to occur. Keep in mind that petrified remains occur only under very unique circumstances. So the first thing that has to happen is that when the organism dies, its remains have to be protected from the environment. So if this organism died, say, let's consider a deer that got hit on the side of the road, its remains are not likely to be petrified because scavengers will come in and maybe take a leg away or chew on some of the bones for sustenance. Or even then, if they're not chewed up, those bones will be decayed through the process of weathering. Rainfall will slowly dissolve the minerals in those bones. So first off, those remains have to be protected. So typically when we find petrified remains, these are organisms whose bodies were either buried in a flood, so there was a flood, caught the animal, and it was buried, or maybe it died and sunk to the bottom of a pond or lake where the oxygen levels are very low. So those are some examples where we typically find petrified remains. And then those get covered up with debris. The second thing that's going to happen, before I move on, here we have the same thing with wood, so don't get the idea that it's just animal remains. Here we have a tree, and eventually you get that tree being covered by sediment. One other example where remains are protected quite well is after a volcanic eruption. So if you had a large amount of ash settling over those remains, that would also very effectively protect those remains. The second thing that's going to happen is that as water percolates through the soil, so here's our piece of wood that was buried, and we have some sediment built up on that. As it rains, or as water percolates through the pond or whatnot, it's going to pick up minerals. So those minerals are going to dissolve in the water, and when we talk about those minerals, typically they might be silica, iron, glass, sulfur are some of the common minerals. And those will eventually crystallize within the pores of the remains that are left behind. So when we look at this idea of crystallization, so when the wood or bone originally is present, you've got the spaces within the wood. This would be the cell within the wood, or this might be the pores in the bones. As the water goes down, the water will get into those pores, and then as the water evaporates out or dries out, the minerals that were in that water will crystallize within those pores. And eventually, that will then get crystallization occurring. And finally, the original material will decompose and is also replaced by crystallized minerals. So when we find a fossilized dinosaur bone, realize that that's not the original calcium. That original calcium was dissolved away over time, just like remains that are of animals that are on the surface. One thing that we want to make clear of, that students often get confused. Some students think that water gets into these pores and the water crystallizes. For water to crystallize, it actually freezes. So it's not that water's freezing and crystallizing within these pores, it's that the minerals that are dissolved in the water crystallizes in those pores. So that's what's occurring through this process of petrification. So in some cases, we can get very well-preserved specimens. These are two of the some of the best preserved specimens of dinosaurs that we found. So this specimen in the upper left, actually both of these are believed to have died and actually dehydrated, dried out, prior to being covered in a flood type event. And you can see here we've got one of the duckbill edmontosaurs, one of the duckbill dinosaurs. And in fact, when they did X-ray examination of this organism, they could actually see some of the where the internal organs were present. In this dinosaur down here, a nodosaur, closely related to the ankylosaurs, you can see the outside surface is very well preserved. So certainly on some of these we can even see, here you can see patterns of the skin that are well fossilized. And by looking at the patterns of the skin, we might be able to infer some of the stripe patterns, whether the organism had stripes or was a uniform color. We might be able to infer some of that. But we would know none of this had it not been for the fossil record.